Why hello lovely friends, Jen Foxbot here for another edition of Math Mondays, yeah! Alright, so glad you are here to join me. We are going to talk about the Pythagorean theorem. Specifically, we are going to work through one of the proofs of the Pythagorean theorem. So there are a couple of things that I love about this equation that applies to right triangles. So when you have a right triangle, you have a hypotenuse, we're going to call this C. You have a base, I'm going to call that B, and you have a height of the triangle that we're going to label A. And so for every right triangle, the sum of the squares of the shorter sides, or A squared plus B squared, equals the square of the longer side, the hypotenuse. And so what I love about this equation, first of all, is that it shows up all the time, and it's super, super useful, but it was discovered over 2,000 years ago. What? And we still use it. So that's what I love about science, is that you never know what sort of thing you might come across or discover that will be super useful for folks down the line. We really embrace our ignorance and ask the hard questions, and then try to pursue answers and truth as much as possible. And so folks were doing this over 2,000 years ago, and we still use it today. It's so rad. So the story goes that Pythagoras came into his classroom and asked his students if they would rather have a gold sheet made of the areas of the two shorter sides. So if I were to draw kind of little squares that had sides of B and sides of A, and then a larger square that had sides of C, Pythagoras asked his students, would you rather have gold sheets made of the two smaller squares, so you get both, or the one bigger square? And this is one of the rare instances where it doesn't matter what you pick, you both win, because it turns out they're the same. So this is the proof that Pythagoras, or at least the one that Pythagoras gets credit for, it's unclear if it was actually Pythagoras or one of his students, but the sum of the areas is a really useful proof, and I would definitely encourage you to do it by hand. So use some graph paper, draw a triangle, and then use the squares to help you make, the squares on the graph paper to help you make squares of lengths A, B, and C. And then what you can do is you can cut the squares up and try to fit the two smaller ones inside this bigger one, and then you'll see that this is indeed true. But since I can't cut my my chalkboard up into little pieces, for better or for worse, I'm going to do a different proof. And there is actually a way to do this proof just purely with angle theorems and stuff like that, but it can be a little complicated. So I want to go a little bit simpler route. So the way that I'm going to do this is I'm going to draw a square made of 4 of these triangles. So bear with me, this can be a little bit tricky to draw, but I'll do my best. Okay, so again, the hypotenuse of our, or the length of one of the sides of our square is, we're going to do this. Wait, is that, oh, that's way too long. I'm going to try and get this to work out. Boop. And then that. Okay. Oh, okay, that turned out okay. Not perfect, but you get the picture, hopefully. Okay, so then in this case, the base is still B, and the length, the longer side, this side, is A. Okay, so now we ask, what is the area of this shape? It's made by 4 triangles, and it has a little hole in the middle. So the first way that we could find the area is pretty straightforward. I'm going to erase this to give myself a little bit more space. So we could just say, well, we know the area of each of the 4 triangles, so let's just add them up. And so in that case, the first method would just be to multiply 4 times the area of one triangle, which is 1/2 base times height, or B times A, and then that would give us 2AB. Pretty straightforward. Okay, and so now, since we're interested in figuring out this identity, we need to find something with C in it. So the second way that we can find the area of this funky little shape, a square with a tiny square hole in the middle, is to say, okay, well, the area is equal to the area of the total square without the whole. And so in that case, it would be c times c, or to write it more succinctly, c squared. And then we would subtract the area of this tiny little hole. And just a quick aside, so we want to find the side length of this square. I'm going to call that x. So let's expand this out really quick. So the whole length of this longer side on our triangle is a. That's a. And it is intersected with the base of the triangle to give us a leftover remainder of x. And so this is going to be b. And so the length of x is just the total length of a minus the length of b. Cool. So then in that case, the area of this smaller triangle, area of tiny t, or tiny square, equals a minus b times a minus b, or just a minus b squared. So then the area of the bigger triangle, sorry, not triangle, square, the area of the bigger square is the total area minus the area of the tiny square. So c squared minus a minus b squared. Cool. Now let's expand this out. So we're going to get c squared minus parentheses, a squared minus 2ab plus b squared. I've done these things a million times, so I can do that in my head. If it helps to write it out, go for it. And now we're going to simplify. So we get c squared, we distribute the minus sign, minus a squared plus 2ab minus b squared. Okay, cool. So now we have an equation with c in it. And since these two areas are equal, let's set them equal to each other and solve for c. So now I'm just going to write 2ab over here. And we want to move all of these terms over onto the other side. And since this is kind of an introductory topic, I'll quickly mention that to cancel the term on one side, you just add the term over here. But then you have to do the same thing on the other side, right? Because your equation has to be kept equal. So by doing this, you're just rewriting the equation. It all stays the same conceptually and theoretically. But we're just moving things over so that we can get c by itself. Okay, so when we do this, we're going to move all these terms over. The signs are going to switch because to cancel, we have to add the opposite. So what we're going to end up with is 2ab, actually, I'm going to write c squared by itself. So we add a squared, so we're going to get 2ab plus a squared. We'd have to subtract 2ab. So on this side, we have a minus 2ab, and then we add b squared. Look at this. So these terms cancel, and we're left with c squared equals a squared plus b squared. Woohoo! Party on! All right, so that's it. That is one of the proofs of the Pythagorean theorem. There are half a dozen, maybe more, different ways to prove this same identity. This is a very powerful and useful equation, and so folks have been running through the various ways that you can show this to be true. There are many of them. If you're interested, I definitely recommend looking them up and running through them on your own. My favorite way to do this is with paper, or if you're lucky enough to have those little, when I was in elementary mathematics, we had these math toys that were little squares that were in ones, tens, and hundreds, and so you could use that to show this area thing. Or you could just cut out different triangles and use that to like actually do this square thingy. Cool. So I'll leave it there for now. Please let me know if you have any questions on this particular proof or any of the other Pythagorean theorem proofs, or if you're curious about how this applies in general, how might you use this in a problem, etc. Please feel free to leave a comment. And then, of course, send me your math questions and we'll tackle them together. All right, thanks very much for watching and we'll see you next time. Bye, friends!